Um, they do mention in this section too, I don't know when exactly we get, can't remember when we get to using these, but really this is all pretty much good news because, you know, we're talking about the derivatives of vector functions. They follow pretty much the rules of differentiation that we know and love. For example, if I'm doing the derivative of a u vector plus a v vector, well, it's differentiation. Well, it's for addition, it really doesn't matter, but yeah, if I'm doing the derivative of two vectors that are added together, you're just going to do the derivative of each vector and add that together. It's one way to do it, I guess. There's other ways, but so that's what I'm saying. It follows the same rules. I mean, subtraction, same thing. Just a couple of the others. I don't know if I'll mention all of them here, but some we may need later on. We'll call them up, but it is good news. So this is just saying, well, all right, if I don't feel like multiplying that constant n to my vector, I can just do the constant times the derivative. So that's also falls in line there. Now, when I get to multiplication or dot product or something like that, well, let's just think about it here. Now, this is just saying, well, let's take a function. This is not a vector, this is just a function. So it's just a specific function times a vector. So again, if I don't feel like multiplying that vector, that function inside the vector there, because I could do that, but if you just look at it from the derivatives perspective here, and just keep it that way, that's multiplication, isn't it? So guess what? Product rule. F prime of t times vector u plus then f of t times derivative of u. So they line up pretty well. And it works, like I said, I mean, this isn't times, this is a dot product, because it's two vectors. And again, if I don't feel like doing the dot product there, so I've got two vectors there that are dot product of those. So if I don't feel like doing those, I can, which probably easier just to dot product those because that's just a number, but anyway, or a single value, single function. But anyway, but it is, as far as derivative is concerned, it is from the perspective of multiplication. I would do the u prime vector dotted with v plus then the u vector dotted with the v prime vector. So those, I said that would probably be the harder way of doing that one if you think about it, but anyway, just be aware. So yeah, so the same rules, sum rule, product rule, those still hold. Okay. All right. Now, there's others, but we'll bring them out as we get them here. The second derivative is also good news because our second derivative of our r vector is just as before. Let's write it this way. You just take the derivative of the first derivative. So that's all good. Okay, so let's just do this little problem I got up here. So R of t is 6t, comma t squared, comma t cubed minus 4. Okay, number one. Find R prime of t. For me, it's easy to forget that. I'm doing the derivative because I do that vector sign, and then I've got to learn to do the derivative too. So forgive me if I forget to sometimes do that. That's probably not a good thing to forget because two different things. But anyway, it's one of my struggles. All right. So, but it's easy. The derivative is just the derivative individually, 6, 2t, 3t squared. Start us off. All right, number 2. T vector evaluated at 2, also known as the unit tangent vector. Let's do our unit tangent vector at 2. All right, so remember, unit tangent vector at 2 or wherever is just the derivative vector divided by its magnitude. It's the unit vector associated with the derivative vector. So that's why I had to do R prime here. So R prime is this, so R prime of 2 would be, just plug in t is 2, so that'd be 6, 4, and 12. And then we're going to divide that by the magnitude of that, so that's 36 plus 16 plus 144. So that's 6, 4, 12. What does that give me? Square root of, I don't know, because I didn't write it down. Somebody punch those in for me. It'd be 150, 186? Yeah, square root of 186. So now we're going to write that.
196.
196. Just checking. Okay. Oh, that's nice. Didn't square 196, 16, 14. Yeah. It's feeling a lot like a Monday here. Oh, that works out nice. All right, 6 over 14, I probably shouldn't do this, but all right. 6 over, so 6 over 14, is that 3/7? 4 over 14, 2/7. 12 over 14, 6. So it works out pretty nice. So that would be the unit tangent vector at 2 anyway. And then thirdly, let's do here an R, excuse me, R prime cross R double prime. Yeah, so those are two vectors, so we can do the cross product. All we need here is just the, we got the R prime, so what's the R double prime? Well, it's just, R double prime is just the derivative of first derivative, so derivative of 6 is 0, derivative of 2t is 2, derivative of 3t squared is 16. So I want to cross product those together. And one way of doing that is line up in this determinant here with the ijk on top, and then the r prime, 6, 2t, 3t squared, with the 0, 2, and 6t. Do that kind of as a determinant. I mean, there's a formula, but that's, I don't remember it. So this is the way I remember it. All right. So what do we got there? Well, it'd be I times the determinant there, 2t, 3t squared, 260, I'll write it out since, and then minus the j would be the determinant 6 3t squared, leave the middle out there, 0 6t, and then the k times the determinant, leave off the last one here, 6 2t 0 2. So that'll give us I times 12t squared minus 6t squared, and then minus j, works out pretty nicely because that would be 36t minus 0, and then the k is 12 minus 0, yeah, 12 minus 0, 2t times 0. Yeah, so we get, what is that, 6t squared I minus 36tj plus 12k. Or, if you write in the other notation, 6t squared minus 36t, 12. So that'd be a cross product there. And, that would probably come in sometimes, computation we might need sometimes. So have us do that. Last but not least, finish it up here so we can start clean next time. Yeah. Integrals and vector functions. Again, good news. If I do an integral from a to b of an r of t dt, good news is the integral, you just do the integral of the corresponding parts. So you do the integral, I usually use the ijk here. So it'll be the integral, so r of t is f of t, g of t, h of t, 3 dimensions. So just do the integral of the f of t, that's times your I. So the integral of a vector function comes out to be a vector function. But it's, again, fairly straightforward. Yeah. It's just like you would hope. You just do the integral of the corresponding parts. So let's say I've got r of t is 2 cosine t I uh, 2tj plus t over t squared plus 4k. So let's find the integral from 0 to pi over 2 rt dt. Finish this up. Okay, so yeah, just like we would hope, 0 pi over 2 rt dt. Yeah, just going to 0 pi over 2 cosine t dt. That'll be the I part. Then I do the integral 0 pi over 2 of 2t dt for the j component. And then the integral 0 pi over 2 t over t squared plus 4 dt, that'll be your k. So it's just pretty much like we'd hope. Really, the only tricky one is the last one. Yeah, so that's just simple antiderivative. Antiderivative cosine is sine, so it'd be 2 sine t. Evaluate that from 0 to pi over 2. Right? Just straightforward antiderivative. Antiderivative of that, power rule, be t squared, so divide by 2, so it'd be just t squared from 0 to pi over 2 times a j. So the only thing is you got a bunch of integrals to do. If you've got 3 dimension, you got three integrals to do. That's just drop that. And then bring up the last one here, because yeah, what we see there. It's not just a direct one, is it? If it was 1 over t squared plus 4, it'd have anti-derivative tangent inverse, right? But with that, as it is, your substitution, yeah, u equals t squared plus 4, du is 2t dt, so d over 2t. I'll make that little u substitution there. I will have just 1 over 2u, right? Which is, that is a direct antiderivative. What is, it'd be 1/2 of natural log. 1/2 natural log. Okay, I guess we can go and do it. So it'd be 2 sine of pi over 2 minus 2 sine of 0. Easier just to write, do these integrals separately and then bring them together. But that would be pi over 2 squared minus 0 squared times the j. But over here, like I said, that'll be 1/2 natural log of u, absolute value of u, but we're dealing in positives, and we're doing t squared plus 4, so what do we got there? Sine, is that 1? 2 times 1, so that's 2i. The sine is 0, 0. Be pi squared over 4 times the j, because 0, 0. And then here we'll have 1/2 ln of, it's not a nice little thing, it's pi squared over 4 plus 4, okay, minus 1/2 ln of 4, plugging in 0. That's okay. And I don't think we can combine those, I guess, but what would we get if I did that? Just to finish it off. If I did that, that's fine. But, so I can do 1/2 ln. So I've got an ln minus an ln, so that'd be divide. So I divide by 4. It'll be pi squared over 16 plus 1. So I divide that by 4, it'd be times 4. Divide that by 4, you got the 1. So either one. Okay?